Hello everyone, welcome to our first class on calculus. In this class, we're going to introduce about calculus, what is a real number. So here we have the definition, so-called short definition of calculus. Now, calculus studies it's actually the sub-branch of mathematics, and it studies the rate of change. So the rate, it also means the slope of a curve. So what is a curve? Now, a curve can be anything, right? So if I draw some curve, it is a curve, and if we put it in the coordinate system, and this is a function. We usually can denote it as f of x. So f is actually short for function, and our input, which we can also denote as y. So y equals f of x. Now, if you look at different points on the curve, so if we choose any point here, correspondingly, we have the value of y. So the calculus or the derivative of this curve means that if I draw a tangent line that just passes across this line and stays in parallel to the point on the curve, then this denotes the slope means and what is rate of change. So across the whole line, you see that the rate of change is actually differently, or the slope seems to be horizontal, versus this point is actually about 45 degrees. So that's a short note on calculus. One is differential calculus, one is integral calculus. So when it comes to differential, for the same example we have earlier, now if we draw x-axis and y-axis, and if I draw a curve which looks like an exponential curve, So if then the differential calculus means that we're interested in the slope of the curve, which is denoted by the tangent, as we said earlier. And back to the rate of change, which is could be adding arbitrary length up to this point, and correspondingly you have the change in y here. So this is a new point. So I can denote this distance as so-called delta x, and this is delta y. Just means that this is, so I have a corresponding change in y. So now the slope can be denoted as the division of these two terms, right? So the delta y divided by delta x, and we can denote it as denoted as the derivative of x at this particular point, x0. So if I denote the derivative or the slope of curve at this particular point, we can put it also denoted as like this. And so this line is our tangent line, and this is also the formula in terms of how we so this is more essentially about differential calculus. Now we'll come to the integral calculus. So if we draw another curve, an area of under a curve. So this is again the same curve, right? Any curve, and this is x, this is y. Okay, equivalent to so the area under the curve means this region, right? So in this region, how big is the area? This is has its applications in many areas, and we're going to talk about it also. In this particular case, how big under the curve? How do we get to that particular number? So it also can be has a starting point A, for example, and an ending point B. Right. Now, so let's talk about another, which is very common, which is the real number. Real number can take in many forms. For example, the numbers we usually deal if it's integer, then we can say it could be -1, 0, 1, or any integer number. Right. So it can also be rational number. Right. Rational number means it can be a fraction, 0.8, 0.3. It can be a quotient, for example, 1/2, right? So we can express it in both ways. It can also be a irrational. So for example, for those who cannot really express in full details, one for like infinite length, and for example, the square root of 2 and the Euler's number E, which we're going to talk about more later. So it basically covers any number we normally use in terms when we talk about real number. So one number between 0 and 2. And of course, if you can pinpoint one number, then we can always pinpoint another number. So and infinitely small addition. The decimal points we have. This is 0.5, and then we can find another point 0.51, 0.512. So naturally, the answer is that there are infinite number of real numbers in this range. Now, so more on fractions. This is going to be just a short review of the. Say we have the expression here, k times a divided by k times b. So in this case, we can usually simplify it as a over b, and that's because we assume k is not equal to z, is not to 0 because b lives in the denominator. one more. So A over B plus C over B. Now we can usually express it as A plus C over B, add the numerator together. Now, if A over B is 0, we know that, of course, B cannot be 0. Right? So this is our inference based on the expression here. And also, A should be equal to 0 because B cannot be exercise if we have this expression, which looks a little bit complicated. Right, 2x plus 8x squared divided by 4x. Now, what we often would like to do is to evaluate what if x equals to 3. Now, to give a shorthand, we usually express this f of x. Right, so input is x, right? Output is the whole value of fx, which is this expression. Now, how do we do this? So we can just plug in. So f of 3, which is x equals to 3, can be expressed as 2 times 3 and 8 times 3 squared divided by 4 times 3. So I'm not gonna get the calculation all the way to the end, so but you get the idea. Now, more on decimals. So decimal just talk about, for example, square of root of 2 is 2 to the power of 1 over 2. So this is the power. And we can also express this sometimes like this, right? It's easier to write. Square of x, for example, if it's equals to a, we know that, of course, this implies a should be bigger than or equal to 0 because the square of something cannot be negative, right? And positive or negative square root of a. So this is just a basic rule of algebra. That also means that now x can be actually anything, right? X does not need to be positive or negative as square root of a or x equal to negative square root of a. That's how we write. You can write in this way or you can write in this way, right? So now a few exercises, true or false. First one, because of the distributive rule, now C, when we times it, we should multiply C to each element in the brackets, in the parentheses. So it should be AC plus BC, right? So this one is false. Now, next one. So when we negative 2 and negative a, when we time them together, it should be 2a, right? But however, because minus 2 is already multiplied together with negative a, then should not go in the multiplication of it's resting this way, so the mark is false. Now, next one. So just to mention that we can only collapse the summation together, collapse the summations together when the denominator is actually equal. So because we're not sure if that equal, then it's not actually something you can apply as a universal rule. So it's also false. The last one. So we have the x minus 2 is equal to 0 or the other thing is 0, then this happens, which of course makes sense because if any one of them is 0, then this is also 0. So this is true. Now, what is a function? So a function is actually very straightforward. It's actually a mapping rule that takes us from x to y, right? Because we can also express y as f of x. So this is a function, and it's actually, in principle, a mapping rule. So it maps. It's a mapping, or it can be also called a projection. So it look at x if it lives in some space and y lives in another space. So the projection should follow some strict rules. One is mapped to one and only one point, right? So, for example, this guy maps to this guy, and this guy maps to this guy as well. That's fine. So we can have multiple points as the space of y. So this y, this x. It cannot happen that the same points map to multiple points in y. So this cannot happen. Otherwise, it's not a function. The space of I, we can usually call it a domain. So this y, we call it range. So how would y, what's the range of y? So we talk about the space of y. That's the space it lives in. So that's our function. It's fine if we have no candidates input points mapped to this point, which is totally fine. Now let's understand more about functions, sort of mapping rule. So given the x, if it's 0, then y is 0, and if it's 1, it's 1. Of course, you can guess like what should it be, what's the relationship be. It's very intuitive. If we plot it on the graph, then we know that this is exactly how a graph is normally plotted. So we'll first find the potential candidate points. Right? So I'm connecting using a straight line. So you have this straight line here in between different points. So this is how it's actually plotted. And when you think about plotting a line, it's not really that's default plots it on a graph. Just another note to mention here is that just I mentioned as y, if we express as a function, it's a function of fx, and in this case, it's x squared. So or output, it can also be the dependent variable, right? So dependence variable because it depends on x targets or the response. And now the x is usually called the independent variable, right? It's because it's the input, it's the source rates in statistics and or a feature. Right, if later you go into a field of machine learning, f itself, just we call it as a function. It can also be a mapping rule. It can be a projection, or it can be also be called a hypothesis, right? So use to describe the relationship between x and y. So now let's look at the codes in Python. I'll share my screen now in the Jupyter Notebook. So this is the place where we can actually do coding. So if we move up, if we move up a bit for describing x. So if you see here, now let me expand the space. Okay, so let me share my screen again. All right. So now if I look at this code environment, so this is a tool called Colab. This is from Google. It's one of the, so we have this relationship y equals fx and equals x squared. So when we think about plotting the graph, of course, we need the corresponding coding and the elements for x. So basically everything here is can be thought of as a function. So here my 5, and I'm converting it to an array. So this is just how Python works in terms of the format of the numbers. So if I play it out, this is my inputs and this is the output. So they just have the elements in y as well. And next, I'm just calling these two lines to plot to tell Python that I want to plot x and y, and actually quite intuitive. And later you'll learn more in other courses in terms of computing using Python. We can also do this more elegantly, right? If we know already the this rule, this is for define a function where the output or the return is actually the square of x. This is short for this the sort of exponential of just the square of the x in the any number, not just the numbers we saw earlier. So for example, in this case, I pass in 2.5, and it will evaluate, it will execute this command based on the definition I have here. And more flexible, we can input anything, it will output the corresponding results. So one thing to note that I put here is interpolate. So because 2.5 lives in the space of range of x, so x because it lives in 0 to 5, then 2.5 is actually within the sort of observed range. Now, what I mean by extrapolate is that it's actually living outside the space, but it's not really that reliable. So that's something we usually look at more carefully when we think about extrapolating beyond what we observed already. In this case, it's still we can calculate. Right. So now short note about functional symmetry or symmetry of the function. So we see that x is even if we see that f of x equals to the f of equal to the absolute value of x, right? So if we put it on a graph, it would be something like this. Right, so if you take a point in, for example, this equal 2, it's true that, of course, the property of fx, and it can also be fx of x squared, and it can also be something like this. It's also symmetrical around the y-axis. And some other example, cos of x, and of course, it's something like this. Then it's also symmetric around x. So the function can also be equals to the negative of fx. Sorry, it should be the negative here. So basically, we move the negative outside of x equals to the cubic of x, right? So actually, so if we look at the graph here, is something like this. Then if we say x is equal to f of 1 should be 1, and f of negative 1 should be also negative 1. And then if we add a negative sign, that is actually the negative to mention briefly. Function also be decreasing or increasing. So if function, we see that the function is increasing, then it can be something like this. So from a particular range, for example, from what it looks like, and correspondingly can be decreasing as well, right? So let me just redraw a bit. All right. So it's decreasing, strictly decreasing, right? Okay, so if you look at the function of f(x) equal, so it's 0. So first it's decreasing, then it's increasing. So this is the trajectory of f of x square. Utility test called the vertical line test. This is how to help us detect if a given curve is a function or not. So for example, if a definition of a curve given any points, there's a corresponding mapping in the y-axis. Right? So this is definitely the function. However, if we look at another curve, something like this, right? So if I give a input value in the x, now if I draw a vertical, which evaluates our condition earlier, which breaks our condition earlier. So this is not a function. Now, a few exercises. So if you look at the function here, x to the power of 3, then we can evaluate corresponding to 27. So basic evaluation here, if you got another one, should be 0, and if it's 2, then it should be 8. So this is just the simple evaluation. And if you look at the domain and the range, so in, like no restriction, right? So we usually expect it's like negative infinity to infinity. So this special symbol here means it belongs to, right, this range. The range of a function is refers to y, and y is also lives in the space of negative infinity to infinity. Basically, you can take out any value, right? However, if you look at the square of x, now x cannot be of course y itself is also the square of something, and in this case, it should also be something like this. Increasing, but slowly the slope is actually decreasing, because now if you look at it big, the sort of the effect of taking the square root is actually becoming more and more obvious. So it's not that it's not increasing that fast. Now let's look at something else. So a few notes about the Euler's rule. So we see that's infinite 2.71828. And the way how we get is that we look at this expression, this particular expression. So we plug in different numbers of x. So if x is very small, y, then we see the value of this expression changes, and it sort of converges to this guy. This is the ultimate value. And if we express it in the more mathematical term, we see x to the power of x. And if we take x to the limit, which means that x goes to infinity, right? So if we have an infinity number, then we will express as lim. Lim is that the value of this expression is going to be the value of e. So this is the definition of the number of e. So why it is important? It's important because it's also used to calculate the value for after some time. So, for example, if you have some money at 0, for example, 1,000 in the bank, and then we actually add so the interest rate section is that after a time period of t, and we have interest rate of r. So the continuous, so this continuous compound. So what continuous compound means is that any interest that derives from the dollars is actually reinvested to the principal itself, and then it's used to grow more interest. So if we want to know at any particular time point t, it could be 1 year, 10 years later, if we have rates of r, then the value of the asset at time t would be this one. So as 0 times e to the power of r times t. This is actually a very e is actually used, and there's a way to derive this formula based on the intuition we have earlier. So we'll talk about more later in latest class, and I think that's it for today's class.